Section 11.4, the binomial theorem. Just a heads up, we are moving on from sequences in series. All right, the first thing we're going to do in this section is review what a binomial is. So it says, recall that a binomial is the sum or difference of two terms. So for example, I'll write some binomials down here. One of the simplest binomials you can possibly have is something like x plus y. Okay. Again, it says a binomial is the sum or difference of two terms. Terms are the pieces separated by addition and subtraction. So here, x is the first term and y is the second term, and you're adding them up. All right. So another binomial might be r squared minus s. Okay, so here you have two terms. R squared is the first term, S is the second term. You're subtracting them. Okay, they can be more complicated. Maybe you have 3 minus y over 3. Okay, binomial. Okay, the first term is 3, second term is y divided by 3. You're subtracting them. Okay, I'll give you one more. Maybe we have the square root of 2 times r plus 1 over m. Okay, again, you've got two terms. The first term is the square root of 2 times r. The second term is 1 over m. We're adding them up. Okay, so that is what a binomial is. Okay, so what is this binomial theorem? Okay, well, it's a theorem, but what does it do? Okay, so if you read the second sentence here, it says, in this section, we will learn a method for writing binomial expansions of the form x plus y, that quantity in parentheses, raised to the nth power, where n is a natural number. Okay, so basically, if I asked you to take, I'll just take this last binomial here. If I told you to take this guy and raise it to the 7th power and multiply it out, okay, that's really tedious. If you know the old school way, if you FOIL it out, you distribute it out 7 times. Okay, again, this means you would take this thing, the square root of 2 times r plus 1 over m, and multiply it by itself 7 times. That's a lot of work. Okay, what the binomial theorem is, it is a shortcut for doing this. Okay, if you need to expand a binomial, it tells you how to do it without doing all the distribution. Okay, all right, so let's take a look at how this is going to work. Okay, so underneath this, okay, you see a binomial expansion pattern. Okay, it says complete the following via multiplication. Okay, all we know so far as expanding a binomial is by doing good old-fashioned multiplication slash distribution slash FOIL, whatever you want to call it. Okay, so that's what we're going to do to start this off. Okay, I've got the binomial x plus y, and we're going to compute several powers of it. All right, if you look here, we're going to compute, you know, x plus y raised to the 0 power, raised to the 1st power, the 2nd power, all the way down to the 5th power. Okay, and again, all we know so far, we haven't talked about what the binomial theorem is, so we're going to have to do this via multiplication. Okay, so let's start. Okay, first thing, we've got x plus y. Okay, that's our binomial. It's being raised to the 0 power. Okay, that one's easy. Okay, it's 1. Anything to the 0 power is 1. All right, and now we're going to move on. Okay, we're going to do the next one. Okay, we're going to take our binomial. Okay, we'll raise it to the next power. Again, your power has to be basically a counting number, okay, or 0. All right, so here we've got x plus y to the 1st power. Okay, anything to the 1st power is going to be itself. So this is going to be just x plus y. Okay, and then we'll move on to the 2nd power here. Okay, so x plus y to the 2nd power. Remember what this means. You've got to take x plus y and multiply it by itself. Okay, so we're going to see what that is. You can use FOIL here, where you multiply the first terms together. That's what the F stands for. Then you multiply the outer terms together. That's what the O stands for. then the inner terms, that's the I, and then the last terms, that's the L, okay? Or you can use the box method, okay? I typically prefer the box method. If you're doing x plus y times x plus y, okay, you kind of make a box out of it. You take this first piece here and you make a column out of it. So x plus y, and the signs are important. Everything is positive here, but if you had a negative term, you would take the negative sign with it. And then across the top, I'm going to take the second piece here, so x plus y, okay, and you make a box out of it, and then you just multiply each pair of terms together, okay? So x times x is x squared, x times y gives you xy, y times x is the same thing as x times y, because when you multiply, it doesn't matter the order. So you're going to end up with another x times y, and then y times y gives you y squared, okay? And what you get left with are the four pieces or the four terms that this thing expands into, okay? So I'm just going to write it down. This is going to be x squared plus xy plus another xy plus y squared, and then we can combine like terms. Like terms have to have the same variables raised to the same powers. So we have an xy and another xy, so those guys will combine. This will turn into x squared plus 2xy plus y squared. Okay, so I'm going to go write this in the blank. Okay, so if we expand this guy, this is going to be x squared plus 2xy plus y squared. Okay, I'm going to do this again. Okay, why am I doing this? Because we're developing a pattern here. You're going to see a pattern. Okay, all right, so we're going to move on to x plus y cubed. That means you're multiplying x plus y by itself 3 times. You can also look at it as we're doing x plus y and multiplying it by x plus y squared, okay, which we already know the expansion for x plus y squared, okay? So what I'm going to do over here, this is going to be basically I'm going to take x plus y and multiply it by x plus y squared, which is x squared plus 2xy plus y squared. Okay, that's how I'm going to figure this out. Okay, you've got to distribute all of this out, okay, to get your answer. So I'll do this over here. Okay, all right, so I'll put this in a different color. So here we're doing x plus y cubed, okay, which we know is x plus y times x plus y squared. So this is going to be the quantity x plus y times the quantity from down here, x squared plus 2xy plus y squared. Okay, again, I'm going to do this box method on it. Okay, I'm going to take the first factor that I'm multiplying here and make a column out of it. So this is going to be x plus y, and then take the other factor and go across the top, x squared plus 2xy plus y squared. Again, everything is positive, which is great. So I'm going to make a box here. Okay, multiply each pair. Okay, so x times x squared is x cubed. Okay, x times 2xy is going to be 2x squared times y. X times y squared is going to be x times y squared. Y times x squared is the same thing as x squared times y. Okay, y times 2xy is 2xy squared. And then y times y squared is y cubed. Okay, so this is going to produce, if we were to distribute this quantity out, we would get 6 terms in total. Okay, so I'm just going to write them down, and then I'll look to combine like terms. So x cubed plus 2x squared y plus xy squared plus x squared y plus 2xy squared plus y cubed. Okay, so I just wrote it all down. And now I'm going to look to combine like terms. Okay, remember, like I said, like terms have the same variables raised to the same powers. So here, nothing combines with the x cubed, so I'm going to go ahead and write it down. Okay, so I'm going to scratch it out once I'm done with it. Then I'm going to look for terms that have an x squared and just a y. Okay, so that's going to be this one and this one. So we end up with plus 3x squared y. Okay, and then I need to look for terms that have an x and a y squared. So that's these red guys. I have one term here and then two of them here. So that's going to combine to be plus 3 x y squared. And then lastly, I've got the y cubed. Nothing combines with it. Okay. So this is going to be plus y cubed. Okay, so this is my answer if I calculate or distribute the x plus y quantity cubed. Okay, so I'm going to go write this down. This is going to be equal to, let's see here, this is going to be 3 x cubed, sorry, this is going to be x cubed plus 3 times x squared times y plus 3 times x times y squared plus y cubed. Okay, so I'm going to go back and highlight what we've been getting as our results. Okay, all right, so now we're going to bump it up again. Okay, x plus y to the 4th and x plus y to the 5th. Okay, hopefully you know how to do this. Okay, how you know how to do the distribution on your own. I'm going to pause the video and work these two out on the next page as I have been doing, and then I'll come back and write the answers here, and then I'll resume the video. All right, I'm back. So you can see that I have filled out the remaining expansions. Okay, and I've highlighted the final answer in yellow. If you need to see any of the work, I've got that on the next page. Okay, so I did basically x plus y to the 4th power and x plus y to the 5th power all expanded out. All right, now you can keep doing this. Okay, you know if you've multiplied out higher powers, how tedious it can be. So that's pretty much what the binomial theorem is here to help us with. Okay, since we've done this, okay, we've done this, you know, we've expanded x plus y, that quantity, all the way out to the 5th power. Okay, what lies underneath is a question. It says, what pattern exists for the first and last terms of each expansion above? Okay, so let's do some investigating. Okay, like I said, there should be some patterns that we notice. Okay, so this first question is specifically about, what do you notice about the first term in the last term in each expansion? Okay, let's ignore x plus y to the 0 power for now. We'll come back to it. Okay, let me erase the yellow stuff here so that we can actually write on the answers here. Okay, give me a second to do that. All right, let's see. Here and here and here and here. Okay. All right, so let's start looking for patterns, like I said. Okay, so we're concentrating on the first term of the first and the last term for each expansion. Okay, so I'm going to start with x plus y to the 1st power. Okay, so the first and the last term. Okay, what do I see? Well, I'm raising the binomial to the 1st power. The first term is going to be x to the 1st power, and the last term is going to be y to the 1st power. So it's basically this to the 1st power and this to the 1st power. Okay, the same thing is true of the first and last term in the next expansion. Okay, so if I do x plus y, that quantity squared, the first term is going to be x squared, the last term is going to be y squared. Okay, so basically it's this term squared and then this term squared. Okay, next expansion, x plus y quantity cubed. Okay, the first term is x cubed. The last term in the expansion is y cubed. Okay, again, if you go back to your binomial, it's the first term cubed and the last term cubed. Okay, and this keeps going. Okay, if I go to x plus y quantity raised to the 4th power, okay, the first term is going to be x to the 4th. The last term is y to the 4th. Okay, again, x to the 4th, y to the 4th. Okay, bet you can't guess this. When you get to x plus y quantity to the 5th power, the first term is going to be x to the 5th, and the last term is going to be y to the 5th. Okay, all right, again, it's just your first term in the binomial raised to the power, and then your last term in the binomial raised to the power. Okay, so What pattern exists for the first and last terms? Okay, it's x to the power, so I'll just use n for whatever the power is. This is going to be your first term, and then you have y to that same power. Okay, that is going to be your last term. Okay, that's the pattern here. Okay, if you are working with x plus y raised to the nth power. Okay, all right, next question. What pattern exists for the exponents on x and y for each term between the first and the last terms of each expansion? Okay, so now the question is, do you see a pattern for the exponents in the middle? Okay, so let's go back and look. Okay, again, I am going to start with the, I'll start, it's more obvious with the second power, so let's start there. Okay, all right, so again, we've already looked at the first term and the last term. We're looking in the middle now. Okay, do you see a pattern with the exponents? Okay, so I'm going to write in red here, okay, so you can see it stands out more. All right, in this expansion for x plus y quantity squared, we're looking at this middle term, 2 times x times y. Okay, the pattern that we should notice, okay, is that if you add the powers on the exponents, it should add up to the power of the binomial. Okay, meaning when I look at this middle term, it's x to the first, and then it's y to the first, and 1 plus 1 adds to be 2, which is the power of the binomial. Okay, this happens to all the middle terms. If I move on to the next expansion, x plus y quantity cubed, all the terms in the middle, the powers of the exponents should add to 3. Okay, so if I look in the middle here, I have x squared and y to the first power. Those guys add to 3. Okay, then the next middle term is x to the first power times y squared. If you add the exponents, they add to 3. Okay, then same thing, move on to x plus y to the fourth power. Okay, all the terms in the middle, okay, their powers should add to be 4. Okay, if I look in the middle here, x cubed and then y to the first power, these exponents add to 4. Okay, x squared, y squared, 2 plus 2 is 4. And then the last middle term here, we have x to the first power times y cubed. Okay, the powers add to 4, which is the power on the binomial. Okay, lastly, we see it in the last statement. Okay, here the binomial is being raised to the 5th power. Okay, all the middle terms should have the exponents on their powers, or sorry, all the middle terms, if you look at the exponents, they should sum to be 5. Okay, so we have 5x to the 4th times y. The exponent on y is 1. 4 plus 1 is 5. Okay, and then this term, 3 plus 2 is 5. Okay, this term, 3 or 2 plus 3 is 5. Okay, here the exponent on x is 1. 1 plus 4 is 5. Okay, so that's what we're seeing here. Okay, so the exponents on x and y for each term between the first and the last sum to n in each term, in each middle term, I should say. Okay, so that's what's going on. The exponents on x and y sum to the power n, okay, in each middle term of the expansion. Okay, all right, we're still looking for patterns, so I'm going to jump to page 2 here. The next question says, what pattern exists for the coefficients in the terms of the expansion of x plus y raised to the nth power? Okay, so now it's asking about coefficients. Okay, and if you notice, I have this triangle. Okay, the triangle consists of a bunch of blanks. Okay, we're going to go back to our expansions starting with x plus y raised to the 0 power, and we're going to go all the way down and we're going to write the coefficients, the numbers that we see. Okay, so let me grab the first couple of lines here. I'm going to go back up to my expansions, okay, the final answer, okay, and I'm writing down the numbers that I see. Okay, x plus y quantity raised to the 0 power, that's just going to be 1. Okay, then if we go to the x plus y raised to the first power, there's a 1 in front of x and a 1 in front of y. Okay, so the coefficients are going to be 1 and 1. Okay, moving on, x plus y quantity squared. Okay, I'm looking at the expansion. The coefficients are 1, 2, and 1. Okay, so I'm going to write those guys down. Okay, going to x plus y quantity cubed. In the expansion, I see the coefficients, the numbers in front of the variables, are 1, 3, 3, and 1 in that order. Okay, so 1, 3, 3, and 1. Okay, moving on, x plus y raised to the fourth power. Okay, the coefficients I see 1, 4, 6, 4, 1. Oops, I forgot 1, 4, 6, 4, and 1. I promise we're doing this for a reason. Okay, last one that we'll write down. X plus y raised to the fifth power. 1, 5, 10, 10, 5, and 1. Okay, so this is what our coefficients are doing. Okay, there is a pattern here. It may not be obvious. Okay, so let's read below. Okay, it says with the coefficients arranged in this way, each number in the triangle is the sum of the two numbers directly above it. Okay, meaning the sum of the number to its right and the one to its left. Okay, watch. Okay, this first term of 1 at the top, at the peak, there's nothing above it. Okay, so 1 is kind of like our starting place, as is the second row. Okay, the first couple of rows are all ones. Okay, and then if we go to the third row and you look at this number right here, there's no number to its left. Okay, but there's a number to its right. We have to have both a number to the left and a number to the right in order to sum. If we don't have both numbers, it's just going to be a 1. Okay, that's why there's always a 1 on the periphery of the triangle. Okay, if you look here, and I'm looking, let's see here if I can do this. If I look right here along the triangle, the periphery, okay, we always have 1s. Okay, same thing as if we go this way, we're always going to have a 1 because there's not a pair of numbers to add. Okay, so the periphery of the triangle is always going to be 1. Okay, but if we're looking at numbers on the inside that does have a number to its left and to its right, you sum those numbers. Okay, so for example, let's start with the 2 here. Okay, if I add the number above it to the left and the number above it to the right, 1 plus 1 gives me 2. Okay, then if I start the next row, of course we're going to start with a 1, but when I get to the 3, how do I get the 3? I add 1 plus 2. Okay, and then I move to this number. How do I get it? I add 2 plus 1 to get 3. Okay, the row will end with another 1. Okay, you see the same pattern down here. Okay, the row starts with 1, and then I sum, to fill in this blank, I would sum the 1 and the 3. 1 plus 3 gives me 4. Okay, to get the 6, I would add the number to the left with the number on the right. 3 plus 3 gives me 6. To get the 4, I add 3 and 1. Okay, I end the row with a 1. Okay, the pattern continues. This last row that we did, we start the row with a 1. Okay, to get the 5, it's 1 plus 4. To get the 10, it's 4 plus 6. Okay, to get this 10, it's this 6 plus this 4. To get the 5, it's 4 plus 1. We end on a 1. Okay, that is the pattern that we're seeing in the coefficients. Okay, again, each number in the triangle is the sum of the two numbers directly above it, the one to the right and the one to the left. Okay, this triangle has a special name. Okay, this triangular array of numbers is called Pascal's triangle. Okay, so basically, if you're doing an expansion of a binomial, the coefficients are coming from Pascal's triangle. Okay, if you've ever heard of it. Okay, so that's pretty cool. Okay, so we end here, now that we've seen all these patterns, it says let's find the expansion of x plus y to the 6th power. Okay, so what I'm saying here is we're going to write down this expansion. Okay, I'm not going to sit here and multiply it out like I previously did. Okay, we see all these patterns that have been going on, and that's going to help us to just write this expansion down. Okay, all right, well, the first term is going to be x to the sixth. Okay, the last term is going to be y to the sixth. Okay, I'm kind of scared that I need more room, so let me move this over. Okay, so then what we're going to do, okay, is I am going to write the coefficients. Okay, I'll deal with I'm going to deal with the variables and the exponents. Okay, I'm going to deal with the coefficients last. Okay, so remember the patterns that we did see. So I'm going back to page 1. Okay, the first pattern we just took care of. We know the first term and the last term, what it's going to be. And then after that, the exponents on x and y sum to n in the middle term. There's something else I missed because I forgot to mention this. If you go back and look, okay, the let's start with x cubed here. Okay, when you do this, okay, look at the powers of x. Okay, you're starting with x cubed in x plus y quantity cubed, and as you progress through the expansion, the powers of x go down by 1 every time you move to the right. So in each term, you go from x cubed to x squared to x to no x's. Okay, on the other hand, the powers on y increase. Okay, so we start with no y's, but then we get a y to the first, y to the second, we end on y cubed. Okay, so the same thing is happening in the next expansion. So you start with an x to the fourth. The x powers are going to descend by 1. So you'll go from x to the fourth to x to the third to x squared to x to the first to no x's. And then the opposite happens with the y's. You start with no y's, but then you get a y in the next term, then a y squared, a y cubed, all the way up to y to the n, which is y to the fourth here. Okay, and that same pattern is exhibited in the next expansion. Okay, so let me add to this. Not only do the exponents on x and y sum to n in each middle term, but the powers of x descend from left to right, and the powers of y increase from left to right. Okay, so now that I know that, okay, I can fill in the middle. Okay, my first term is going to be x to the sixth. So that means that the next term is going to have x to the fifth. Okay, and again, I'm so scared of not leaving enough room. Okay, so x to the fifth. Okay, and then the next term is going to have x to the fourth. And then the next term is going to have x to the third. And then the next term is going to have x squared. And then the next term is going to have x to the first. And then the last term will have no x's, okay, but it will end with the y to the sixth. Okay, then you have to put the y's in. Okay, the first term will not have a y. Okay, the second term will start the y's. Y to the first, y to the second, y to the third, y to the fourth, y to the fifth, and then y to the sixth, where you stop. Okay, every term in the middle, okay, if you add the exponents, on the variables, they will sum to 6. Okay, all right, so we've got all the variables and their powers. Okay, since we have addition here, we're adding all the terms together. The last thing we need to do is talk about the coefficients. We can get those from Pascal's triangle. Okay, so all I need to do is compute the next row of the triangle. Okay, so let me see, how many blanks are we going to need? 1, 2, 3, 4, 5, 6. Okay, so we're going to add 1 to that. So 1, 2, 3, 4, 5, 6, 7 is what it's going to look like. Okay, okay. So, all right, so when we fill this in, remember the periphery of the triangle, these blanks will be 1, okay? Now to get the numbers, we need to add, okay? 1 plus 5 is going to give me 6. 5 plus 10 is going to give me 15. 10 plus 10 is going to give me 20. 10 plus 5 is going to give me 15. 5 plus 1 is going to give me 6. Okay, these are the coefficients that you're going to see in the expansion for x plus y raised to the 6th power. Okay, so I'm going to go ahead and write them down. Okay, so it's going to be 1 times x to the 6th times 6 times x to the 5th times y plus 15x to the 4th times y squared plus 20 x cubed y cubed plus 15x squared y to the 4th plus 6 x to the 1st y to the 5th plus 1 times y to the 6th. Okay, so that's the expansion. Okay, just by knowing all these patterns, okay, we didn't have to do all of that work. Okay, as you get practice with this, the patterns kind of become clockwork to you. Okay, so it won't take as long to go through. Okay, one thing I will end on, okay, in this triangle, okay, there's a lot of symmetry. Okay, so like for example, in this line we just did, okay, the middle number is 20. Okay, but on either side there's symmetry. Okay, so 15 balances with 15, 6 balances with 6, 1 balances with 1. Okay, you're always going to see symmetry like that when with the coefficients. Okay, you'll see a coefficient on the left and it'll match somewhere on the right. Okay, so that's pretty cool. All right, what we're going to talk about as we go on now, okay, Pascal's triangle is great and all, but it becomes very tedious, especially if you're trying to do a larger expansion. So for example, if I wanted to compute the expansion of x plus y raised to the 100th power, that means I'd have to go keep writing down to like the 100th row of the Pascal's triangle. Okay, that's a pain in the butt. Okay, so what can we do if we're dealing with these higher degrees of expansion?